This Calc 1 lecture is on area. Based on your conceptual understanding of an integral, that lecture, you should feel comfortable to begin finding area in certain regions. So look at this example. It says find the total area between the region and the x-axis. So let's sketch my x-axis again, and this is a 2 and a -2, and these are, so you can see. So I am supposed to sketch this region and find the area where x is between -2 and 2. So I am looking at this region in here, this region in here and here, and this region in here. So let's sketch this again. So you recall that if you are finding areas that are above the x-axis, that you don't need to do the absolute value of those, and if you're looking at areas that are from the x-axis below that, you need to take the absolute value. Now, I want to draw in something to help us here a minute. I'm going to draw in a representative rectangle, just to talk to you guys about some vocabulary here and to give a precursor for what is coming up next. Now, do you notice any symmetry here? Do you notice that these two regions are symmetric to each other, and these two regions are symmetric to each other? So if I just find my boundaries, I could actually use some symmetry to help me set up a faster way to do my integration. Let's start by finding all 4 regions, well, 3 regions if you count this as 1, 3 regions, and then look at symmetry and set this up another way. Are you guys comfortable that from here to here is -2 to 1? So if I am looking for this region in here, I could set up an integral whose boundaries are from -2, smallest value, to -1. Here is my integrand with respect to x. For this area in here, my boundaries are going from -1 to 1. Here's my integrand with respect to x. Please notice that because that region was below the x-axis, I put absolute value bars. And the region over here is from 1 to 2, same integrand, dx. Now, let's erase here and look again at my symmetry. So we were comfortable, hopefully, that this area and this area were symmetric to this area and this area. So if I want to just find an integral, or two integrals in this case, representing this area, I could use 2 times this area right here, absolute value bars, where did they go? From negative, nope, that would be from 0 to 1. And no absolute value bars from 1 to 2. Again, remember, if the integral is negative, we can take its absolute value. If it's positive, we don't have to do anything. That's getting ready to change in about 5 minutes, but just reminding you of what we talked about when we were learning about the conceptual definition of an integral. All right, let's look at another question. Find the total area between the region and the x-axis. And here is my curve. So let me sketch that in a little bit better. And I'm going from -1 to 8. So do you all feel comfortable that we are looking at this region in here, this region in here, and this region in here? Now, let's go back to that representative rectangle again. I'm going to draw one in here, and here, and here. And let's talk about that. Remember, the idea when we were doing our conceptual definition of an integral is we were putting in more and more and more of these rectangles, and they were getting skinnier and skinnier in width as we put more and more of them in there. And we learned that if we used an integral from our boundaries, we could find the area under a curve. So I want you to do something with me right now. I want you to imagine sliding this representative rectangle right here. It represents one of however many we want to put in there. And I want you to imagine sliding it this way until you get to 1, and then sliding it back this way until you get to 8. I want you to focus on the top and the bottom. In fact, let's make these a different color. The top and the bottom of that rectangle. Are you comfortable that the top of that rectangle, as you slide it, will stay on the x-axis, and the bottom of that rectangle will stay on this curve right here, which is y equals x to the 1/3 minus x? I hope you are. You can do the same thing with the other two little itty-bitty regions over here. You can slide that representative rectangle and that representative rectangle, right and left. Now, to set up an integral here, are you comfortable that I would need 3 of them? One here, 2 here, 3 here. So let's start right here, this first integral. I am going from -1 to 0, and I have an integrand that is x to the 1/3 minus x dx, and that is underneath the x-axis, so I would need absolute value bars there. And to find this total area, I would then add that to this integral right here, which would be the same thing, x to the 1/3 minus x dx, but doesn't need any absolute value bars. And that one goes from 0 to 1 for its boundaries. And then add that to, let's make this a little bit smaller, add that to the integral from 1 to 8 of the same thing, x to the 1/3 minus x dx. And because that one is underneath the x-axis, I would have absolute value bars around it too. Now, I am assuming that with all the work that you have put in so far and all the practice, hours I'm assuming, for doing your integration here, that you would not have any issues doing this. But just in case, let me get you started a little bit. So your work, you would take the antiderivative of an x to the 1/3 minus an x. So you add 1 to 1/3 and you get x to the 4/3. And dividing by 4/3 is the same as multiplying by 3/4. Minus the antiderivative of x would be x squared over 2. And you are going to evaluate this from -1 to 0. And when you do that, you are going to take an absolute value of whatever you get there. And then you are adding to that, I'm just going to get the same integral every single time, right? So I'm going to get 3/4 x to the 4/3 minus x squared over 2, but I'm evaluating from 0 to 1, and I don't need absolute value bars. And I am adding to that the exact same integral again from 1 to 8. And this one, I did need absolute value bars on. So let's do one line of work, and then I will stop and give you the answer. Are you comfortable that when you plug in 0 here for x and x, that you will get 0? And when you plug in a -1, you will get 3/4 times -1 to the 4/3 minus -1 squared over 2. And again, I needed absolute value bars around this. When I plug in a 1 here and here, I'm just going to get 3/4 minus 1/2. And when I plug in a 0, I'm just going to get 0. And over here, I'm going to get 3/4 times 8 to the 4/3 minus 8 squared over 2 minus, and I already know what 1 is because I did it right here, 3/4 minus 1/2. So this all goes together, and I need to remember to do my absolute value bars. Okay, turns out that your answer is 83/4. You guys don't panic on your test. There's just going to be a lot that you need to set up, not so many that you need to find the actual area and do all of your integration for. I'll be testing your integration skills on earlier parts of the test. So let's talk about finding an area between curves. So look at the picture here that you see of a circle with a triangle in it, and suppose that you are trying to find this shaded region in here. Would you guys agree that the area of the shaded region will equal the area of the circle minus the area of the triangle. Does that make sense to everybody? That idea of finding something by subtracting is going to be important to us. So let's say that you are trying to find the area of this yellow region. It's between two curves. It's between f of x, that's this curve right here, and it is, that yellow area is between f of x, the red curve, and g of x, the yellow curve. If I'm trying to find the yellow region, would you agree that, let's get rid of that color. The area of the yellow region will equal the area under f of x, this whole entire thing right here, minus the area under g of x, this whole area right here. Do you agree that if you would take the horizontal red markings and subtract out the vertical red markings and subtract out the horizontal green markings, that would leave you with just the yellow shaded region? I hope so. Okay, let's draw in a representative rectangle here, because I know I need to find the area under f of x from a to b and subtract from that the area under g of x from a to b. Since these integrals both have the same boundaries, and for your thought purposes right now, they're both above the x-axis, I should be able to write this as one integral, f of x minus g of x with respect to x. Now, let's go back to my representative rectangle up here. Couple of things that we want to talk about. You remember that the area of a rectangle is its length times its width. Does it make sense to you that this distance right here is its length? In other words, the difference between f of x and g of x. And are you comfortable that this right here is its width? But I want you to think about what's happening there with that width. Isn't that width changing as you put more and more and more rectangles in there? Isn't it getting smaller and smaller and smaller? So this change in x, that is my dx, which is my width of my rectangle. Back to the length for a second. F of x minus g of x, right here, its length. Do you see that the upper part of this rectangle, right here, and the lower part of this rectangle right here are a way that I can think of the length? The top of the rectangle minus the bottom of the rectangle. The bottom of the rectangle is on the curve g of x. The top of the rectangle is on the curve f of x. That's the length of one rectangle. All right. Now, a couple of other ways that you can help yourself understand that you are finding the difference between the curves is if you want to find this shaded region in here. That is equal to all of this region right here minus that region right there. So that picture in your textbook is showing you again that the integral from a to b, here's your boundaries, can be written as f of x minus g of x, because here is everything under f of x, here is everything under g of x. All right, now what about when I have a region? What if I have a region that is partly above and partly below the x-axis? Guys, you are never, ever, ever again, ever, even on a test, going to have to worry about taking the absolute value of an integral. And I'm going to explain to you why. All right, let's put a line through here just for our visual sake for a minute to separate the area that's above the x-axis and below the x-axis. Now let's draw in a representative rectangle up here, and let's draw in a representative rectangle down here. Let's look at the area above the x-axis. The blue curve at the top is f of x, and the yellow curve at the bottom is g of x. So are you guys comfortable that I could go from A to B? And you know what? Let's fix where B is. All right. Above the x-axis, to find that region, I would take the upper, right here, upper is f of x minus lower, which is 0. And now let's do the purple. And let's say that below the x-axis, my integral goes from A to B. My upper, the top of my representative rectangle, is at 0 minus lower, that's down here, that's my g of x. Now, I would need to add these two integrals together. This integral plus this integral. Let's think about how I can write that. I don't have to worry about the plus 0. I don't have to worry about the 0. So look what I have. I have the integral from A to B of f of x minus g of x dx. So that's huge. You may not realize it, but that's huge. So let's go back to my picture. And let me fix it again over here. All right, I'm going to draw in one representative rectangle. So no more purple, no more green, no more yellow. I'm going to do this with one representative rectangle. Do you see that I can write the top of this f of x minus the bottom of this g of x dx from my boundaries A to B. So this right here, even though part of it's above and part of it is below, it doesn't matter. I can still draw in one representative rectangle and write upper minus lower. Now, visually, here's another picture down here of how you could think of an area being filled in with more and more and more rectangles. And again, all you would need to do is draw in one representative rectangle. Here's its length, here's its width. You would write your integral from A to B, summing up an infinite number of these rectangles. If this curve is f of x and this curve is g of x, you would write f of x upper minus g of x lower dx. Now, I've got another slide here that has a pretty good transparency, and you can see that this distance right here, they're calling my change in x, as that's getting smaller and smaller and smaller. And here's my length, which would be my f of x minus g of x. All right, let's see if you guys are ready for a couple of problems. Did I miss a page? Yeah, I missed a page. All right. So let's put in, this is page 5 of your notes. You are supposed to be finding the area between curves with the given domain. And your curves are y equals 5, y equals the square root of x, and you're going from x equals 1 to 4. So let's sketch this thing. So let's see, 1, 2, 3, 4, 5. So y equals 5. Horizontal line here. We need to sketch y equals the square root of x. You guys that are my students, draw this in the air with your finger. You know what this looks like. So you are graphing 1, 2, 3, 4. All right. So 1, 1 and 4, 2. And it looks like, I should have done that in black, shouldn't I? Let's erase that. So it looks like that, right? Kind of. But I am only interested in the area between 1 and 4. So I am trying to find that area. So guys, when you're doing these problems, the first thing you want to do is graph. Second thing you want to do is you want to shade in the enclosed region. The third thing you want to do is draw in a representative rectangle. So let's draw in my rectangle. Now you need to get in the habit of this. I want you to slide that in your head. Slide it right to left, all the way over to 1, all the way over to 4. Back and forth in your head. Do you see that the top stays on the curve y equals 5 and the bottom stays on the curve y equals rad x? As you slide it, I cannot tell you how important that is. You've got to be able to visualize staying on this curve. So let's erase this. You've got those steps of what I do early on. And now let's set up an integral. Let's talk about our boundaries, our upper and lower limits of integration. We're going from 1 to 4. My upper curve is 5. My lower curve is rad x. We are integrating with respect to x. Now, I want to make one other point to you, and that is, please notice that this representative rectangle is vertical. It will not always be. That's why I am pointing this out to you. So this is an easy one to integrate. Remember, I told you that some of these you'll just be setting up. Some of them you'll be integrating. So let's go ahead and do this integration. We need to think of this as an x to the 1/2. So when I integrate, the antiderivative of 5 is 5x. The antiderivative of x to the 1/2, when I add 1 to 1/2, I get 3/2. Dividing by 3/2 is the same as multiplying by 2/3. My boundaries are from 1 to 4. So let's plug in f of b first. So I would have 5 times 4 minus 2/3 times 4 to the 3/2 minus, let's plug in 1 now, 5 times 1 is just 5. 1 to the 3/2 power is just 1. And 1 times 2/3 is 2/3. So I will have 20 minus square root of 4 is 2. 2 cubed is 8. Five minus 2/3 is 13/3. So this is 20 minus 16/3. I'm going to finish up here. 20 minus 16/3 is 44/3. Minus 13/3 is 31/3 square units. Alright, sorry I missed that page. So let's give you a second, or you pause it, and now I'm going to clean off this page and we're going to do the problem that's actually here. Alright, we are supposed to find the area of the shaded region. Yay, they set it up for us. So we don't have to graph, we don't have to shade, so our step 3 is to draw in a representative rectangle. Here's my representative rectangle, and your next job is to slide that all the way from pi over 4 all the way over to negative pi over 4. Does the top stay on this red line the whole time? Does the bottom of the representative rectangle stay on the blue curve the whole time? Your answer is yes. So therefore you can set up your integral. So your boundaries are going to go from negative pi over 4 to pi over 4. Your upper curve is y equals the square root of 2. Your lower curve, the blue one, is secant theta tangent theta. So you are integrating with respect to theta. Again, this one's not too hard to do the integration on, so let's go ahead and do that work. So this was my lower curve, the blue one. So the antiderivative of rad 2 with respect to theta would be rad 2 theta. The antiderivative of secant theta tangent theta, you guys recognize that as one of your big 6. It's just secant theta. So you are integrating from negative pi over 4 to pi over 4. So when I plug in pi over 4 for my theta, I will get square root of 2 times pi over 4 minus the secant of pi over 4. And when I do f of a, plugging in a negative pi over 4, I'll get square root of 2 times negative pi over 4 minus the secant of negative pi over 4. So this just gives me a rad 2 pi over 4. Secant of pi over 4, that's in quadrant 1. That's the reciprocal of the cosine of pi over 4, or the cosine of 45 degrees, which is just 1 over the square root of 2. And so when I take the reciprocal, I will get the square root of 2. Here, this is a negative square root of 2 pi over 4. Secant of negative pi over 4, this is in quadrant 4. Cosine is positive in quadrant 4, so I will still get 1 over the square root of 2, and when I take the reciprocal for secant, I will get negative pi over 2. So I need to distribute this negative. So I get 2 pi over 4, rad 2, pi over 4 minus rad 2 plus the square root of 2 pi over 4 plus the square root of 2. The square root of 2's add to 0. I have one of these and another one of those. So that gives me a total of 2 of those over 4, which reduces to the square root of 2 pi over 2. So again, that integration was not complicated. It's that level of integration that you would see on your test if I actually ask you to find the area. If I just ask you to set up, you would be going here and stopping. Now, I want to emphasize some things here with you, and then I think I'm going to stop this part of area and do a part 2. When you have a region between two curves, and you are drawing in a representative rectangle given an upper curve and a lower curve. If you draw in a vertical representative rectangle, you are thinking about sliding that representative rectangle left and right, back and forth. When you set up your integral, you will always have upper function minus lower function. So in this case, it would be the antiderivative of f of x minus g of x dx. You find your boundaries from your slide on the x-axis. So we are sliding from, in this instance, A to B. Please notice that these equations are solved for y, not x. So this summarizes the first half of part 1 of 2 videos for area between two curves. Again, never, ever, ever again, ever, 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 do you need to use absolute value to help you find an area.